My name is Baiwu Zhang. So today my presentation title is on attribution of deepfake. First, I will give a little bit background of me. So I'm currently working at a bird company called Twitter. So I'm currently a machine learning engineer at Twitter Toronto office. So I'm in particular in the Twitter health organization, where we basically use technology to drive healthy public conversations. So previously, I was at University of Toronto, completing my master's degree there. At University of Toronto, I studied the intersection of machine learning and computer security, with a particular focus on how do we use technology to combat deepfakes, which is also what I'm talking about today. So today, my presentation will cover some of my research works back in school. But unfortunately, I do not represent Twitter, so I cannot comment on anything that Twitter does or does not about deepfakes. But as Adam said, the hiring market right now is super hot, so Twitter is also hiring a lot. If you're interested, let me know. Yeah. Okay, let's dive into it. So as you may recall, the title of my presentation is Attribution of Deepfake. So first, I will provide a very brief explanation of how deepfakes are usually generated, and then I'll explain why do we actually care about attribution, and also like what motivated us to think about attribution. And then lastly, I will introduce and also explain what attribution means in our context. So deepfakes are usually generated using something called generative adversarial networks. On the left of screen, this is what a generative adversarial network, also known as GAN, looks like. Usually, it has two major components. Like one component is called generator, the other component is called discriminator. So the role for the generator is to take inputs of some random noise and produce output, usually as an image or video sometimes. And the role for the discriminator is to tell whether an image it sees is real or fake. So both of them are usually modeled as deep neural networks in many real world implementations. So during the training phase, what people do is they collect one real image from a pool of real image data sets. And they also collect one fake image or generated image from the generator. Then they feed both images to the discriminator, and the discriminator will try to tell whether which image is real and which image is fake. And then the discriminator will kind of generate two losses, one called discriminator loss to update the discriminator, and one called the generator loss to update the generator. So the purpose for the two losses is, first, for the discriminator, it wants to get better and better distinguishing fake images from real images. But for the generator, the purpose for the loss is to make it better at generating real images, looks more and more realistic as possible. So basically, you have a scenario where those two components are kind of competing with each other, and they are, competing with each other and making themselves better over time. So after training, what people do usually is they extract the generator out and feed in different noises into the generator and generate the additional fake images. And those images, in our context, are usually called deepfakes. So with the with technology advancing on the deepfake front, there are a lot of very fun and interesting implementations or applications emerging. Many of them are actually from the entertainment industry, like the one you said here. This is actually not the real Tom Cruise, but this guy got really popular on TikTok, and it's really fun to watch. And also some other applications are in the advertising industry, where they kind of swapping, different advertisement on the billboard when they're presenting them through the TV. So different people can see different ads but on the same billboard. However, there are also a lot of not so fun applications coming out of it, especially when people are using deepfakes for deception purposes, either for political, with political aims or other nefarious purposes. So that's why I think that's why the reason people are talking about deepfake a lot today, and also that's why that motivate a lot of people to think about, okay, how do we actually defend ourselves from bad deepfakes? Or how can we tell if an image is so realistic but it's actually not real? So to do that, one natural solution people came up with is actually to have some like deepfake detectors. You basically train a machine learning model to distinguish a real image from a fake image. I usually think of that as basically an enhanced version of the discriminator here, where the own purpose of the detector is to tell real image from fake image. Usually that works well, but it has a lot of drawbacks. So that actually brings us to the next thing, the motivations here of what we're doing for attribution. So first motivation for us to do attribution instead of detection is that deepfake detectors are actually not robust. There are quite a lot of research, like many of them are from Google, that they're saying that by changing one pixel of a deepfake image, and then you are able to bypass all the detectors that existing nowadays. This is due to the inherent sensitivity built into all the detectors based on deep neural networks. That's why having a very small change on the image, sometimes less than 1 bit of information change on the image, will make the detector basically fail. The second reason why detectors are not working that well is there is usually a cat and mouse game between the detector and the generator. By that I mean, if someone came out with a new detector and it's really good at detecting fake images, another person can actually come out with a better generator that take into account the new detector and make the generator a little bit better than itself. So in that way, you will have basically arm race between the detector and the generator, and it doesn't really end anywhere. The other reason is deepfake detectors are actually black box and don't provide much explanation. This is due to the limitation of deep neural network, where it's basically not really explainable. This is actually really troublesome for companies or applications where they want to take down posts or take down deepfake posts, which sometimes, without providing a proper explanation, people can rightfully blame you for infringing their freedom of speech. The fourth motivation for us to think about another way of is actually attributing synthesized images will actually pave the road for responsible model usage. I'll explain that a bit later. So moving on, there's also a few limitations on the attribution as well. So similar GANs are difficult to differentiate. If you have two GANs that only differentiate by one single neuron, it's really hard to tell them from each other. And also, it's not always to do attribution in strict integrity case. I'll explain this again later in the next slide. And also, when it's not possible to attribute, we can actually provide plausible deniability. Again, on the next slide. So, okay, so after talking about motivation, I'll explain what we actually mean by attributing deepfakes. So the research question we ask here is, given a synthesized face image, can we robustly attribute the image back to its original generation model? If the answer is yes, that means we can actually do attribution, and otherwise, as a no. So the definition of attribution is if X equals GS for seed S, then X is said to be attributed to G. I'll explain the terminology here. X is the image, the deepfake image here. G is the generator. S is the seed. As you recall, a generator usually takes in random seed and then produce the deepfake. So basically, if we find a G that can use the S to reproduce X, and then we say, X is actually successfully attributed to G, to the generator. Ask a further question to simplify the research question here. We actually divided them into two scenarios. One is called strict integrity, and one is called relaxed integrity. The strict integrity is more like, if we have two images which is only differ by 1 pixel, do we still want to attribute them back to the same model, or we actually say, okay, this image is not actually generated by that model, so we cannot attribute them back. So the relaxed integrity is on the opposite, where we see that if even if the image we're seeing is a little bit different from the actual raw produced image, we still want to attribute them back to the original model. The reason we divided them into the two scenarios is actually in reality, when you see any image or photos posted online, it's usually modified from its raw version, from the version where it was uploaded by someone else, due to either storage limitations, hardware limitations, software limitations, compressions, transmissions, those kind of factors. That's why it's kind of desirable to actually to be able to attribute them back, even though the image was changed a little bit. The other question we want to think about is, is attribution actually possible? We give the formal definition in our work that if there's perfect information, it's actually not possible. That means that if those scans are perfect, they can produce, in theory, any image on the world. So it doesn't really make sense to attribute any image to any GAN, given that any particular GAN can produce all the images in the world. However, again, in practice, that is actually not the case, because GANs are not perfect. They are pretty biased based on their training history and also based on data they use during their training process. So that also says it's good for us because, okay, it's actually possible to attribute them. Okay, that being said, I hope I didn't lose you guys, but here is the last piece of the difficult things to digest. But this is basically how we develop our method to attribute them. So you can actually look at the left part, where there are basically two steps in our process. First is to attribute them back, to attribute any particular image to any particular GAN. What we do is we reconstruct the image on the model with the best reconstruction. So by that, we mean that SG equals to argmean of the distance between the reconstructed image GS versus the original image X. By that, we're basically saying that we want to find it as the seed on the generator G, where it can reconstruct the image, the target image X, as much as possible. So this is possible basically due to the fact that most of the generators are modeled as deep neural networks, which means they are differentiable, so they can actually be optimized pretty efficiently. So this is the first step one. Step two is we repeat step one for every single generator, G, and then we find the best reconstruction among all the generators. So that is saying we repeat step one on all the generators we have on our disposal, and we find all the best reconstructions for each of the model, and then we select a model that actually have the best reconstruction out of the best reconstructions. And then we will say, okay, GX is actually the one that is attributed to X. So in practice, what we do to make it more usable is actually we repeat the process. We repeat the step one for multiple steps, M steps here, to make sure the reconstruction will not be stuck at local minimum. So it can actually reach a global minimum at the expense of more computational resources. I have a graphic illustration here of how that works. So on the left is the basic target image we want to attribute. This is a very handsome guy, but it's fake. And then we have 3 different GANs that at our disposal. We want to figure out which one actually produced this guy. So what we do is, we start the optimization from some random seeds. That's why on the step 0 you see 3 different people that's generated from random seeds. And then we optimize this process to make the 3 GAN approach this target image as much as possible. So as you can see, gradually, as we increase the optimization steps, all 3 of them actually can produce much similar image to the target, compared to itself, right? But however, there is only one, actually, the original model, that are able to produce almost identical image at the target. That's why after step 1000 here, we can very confidently see that the progressive GAN produced the target image. It can reconstruct it very well. That's why this target image was attributed back to the progressive GAN. Yeah. So some evaluations, we found that without adversary, by that we mean in the vanilla case there's no bad guys existing. We can achieve very high accuracy, like over 98% accuracy. With some bounded adversaries, which means the adversary can modify the image under a certain L2 distance, either using the FDSM methods with small epsilon or CW methods. Both of them can achieve over 80% accuracy, which means it's still pretty robust. And then lastly, we evaluate how the method performs under unbounded adversaries, which means the adversary can modify a lot of the image. Some of the modification comes from JPEG compression. It can also come from a horizontal flip or vertical flip, as well as random rotate and random crop. Again, we can achieve not perfect but usable accuracy across all the scenarios here. We additionally performed a very interesting user study to illustrate why this method is actually better at providing some explanation of when people want to come back deepfake compared to the detector methods. So basically, we performed a user study where we presented first on the left is the target image, the original image, and on the right is basically the reconstructions from the different GANs. And we let the users to select which one they think looks most similar to the target image. What we found on the right is actually the user's verdict aligns very well with the algorithms, with our attribution algorithm, which give us a lot of confidence in that our attribution algorithm can use as an explanation to human observations as well. So this is actually pretty promising as a way providing explanation and also avoiding being black box methods causing unwanted troubles. Yeah, so the last thing is actually on the previous method is on the on the relaxed integrity case. However, if you want strict integrity, we actually have proposed different methods where we want to use some immutable and verifiable records to actually record all the images that we want. All the images that we produced by a particular model, such that the model owner can comfortably and also with verification or with a proof to see that our model only produces images, so you cannot blame us for producing images, other than those set of images that we produced before. So this can be achieved by basically register all the seed you use and also append them to a record that cannot be modified afterwards. So one possible solution here is actually use a distributed public ledger, which is something we propose here. This one, just to make it clear, this one doesn't actually achieve the entire complete strict integrity attribution. It only achieves partial strict integrity attribution, where it calls plausible deniability, where I can only deny something that I did not do, but I don't really have any say of something something other people did, but want to be attributed back to me. So this is providing a partial protection to the model owner. Yeah, so lastly, I just want to point out some real-world applications of how the field is actually progressing towards in combating deepfakes. So we actually see very similar or in parallel methods like what we did in our research from the real world, where we want to attribute them instead of detecting them. So one of the most promising one is from Adobe. It's called a Content Authenticity Initiative, where it's actually led by Adobe, but joined by multiple companies as well as journalists, newspapers like the New York Times. What they do is they actually record all the modification records on a particular media. That means when the media was captured, they keep a record. When the media was modified, for example, in Photoshop, they will keep all the records of how the media was modified. And then they will, at the end, when the media was presented to the user, all the modification will be registered in the metadata, so the user have a very solid, very clear idea of, how the image that I'm seeing right now differs from its original form. So this project is gaining a lot of attention recently. The other one is from Microsoft. This one has been going on for quite a while. It's called Photo DNA, where Microsoft record fingerprints of the child pornography in the image and keep a database of it. So when people want to query about it, they can quickly find whether some image was involved in child pornography as a registration, as a way of registering that record into the database. So yeah, this is like basically two methods that's existing right now, along with the many detection systems that people are proposing.
Obviously, we've got kind of deep fakes for audio and images. Is there anything going around in kind of an audio content, kind of deep fake audio, or anything you're aware of at the moment?
Yeah, I know actually. There are also there's quite a lot of spammers that actually using deepfake audio to fool people and to trick them into sending either money to them or do something else. That was a case in the UK. I think the spammer pretending to be their CEO of a company, and they actually got over I can't remember how much, but quite a large amount of money wired to the spammer, and so. To do that, I think people are actually noticing that's actually happening with with more often than before. And I know a company, a startup company, that actually thinking about how do we incorporate that kind of defense in the corporate security realm to make sure to incorporate such systems into the pipeline where people differentiate real calls to spam calls. So I'm not sure that's the audio segment is as popular as the image segments, but there are definitely companies that are looking at this right now.
Is method one computationally expensive?
Yeah. So So basically what we did is we incorporate some flexibility into the methods where you can actually choose your accuracy based on the computational resources that you have. So that's why you can basically make a trade-off between the computational resources versus the accuracy you want to achieve. And again, if you want really high accuracy, there's indeed quite a lot of computation you have to do due to the optimization steps involved here.
When trying to determine which model created a fake, how do you know how to alter the input to the different models to get close to the desired fake? Can you use black propagation for that?
Yeah, if I understand this question correctly, I think basically we have separate optimization for each of the different models. All of them are in disjoint. And then we indeed use backpropagation to optimize the loss to find basically the best seed, the best input that can reconstruct the image as close as possible. So yeah, backpropagation is the method we use here.